Hi. This is the executive black belt supplement on logistic regression, and this is covering slides roughly 137 in your binder all the way to about 150. So starting at number 137. This is a supplementary lecture. Now, what I wanted to talk to you about in this one was really the logistic regression, and I want to be clear on this. This is really an intro to logistic regression, and I think the reason why you'll see it's just an intro, and why you'll want to keep it that way at the moment, is that there's a bit of a conundrum. So on the one side, I think when we give an example or two, you'll say, you know what, this really applies to a lot of things, and I could really use this. And that's great, but to really master it, you need to know a little bit of theory, and unfortunately the theory is some of the tougher stuff that you'll encounter, certainly in a black belt class. So we'll give you a little bit of the introduction into that theory, but more importantly, let's tell you the setting that makes a lot of sense here. So, for example, in logistic regression, the setting looks very, very similar to what we've already covered in regression, except our inputs could be either cats or nums, can have multiples or singles, but our output is a categorical variable, and in particular, a binary one. So in other words, a 1 or a 0 or a yes or a no. This is applicable in a lot of different cases where we have outcomes where we can measure them only in the sense of when somebody acts upon something or doesn't. It's often it either happens or it doesn't. Let me give you a few examples. Perhaps you might run a call center, and you may be interested in looking at a number of waves of people who come in to do training, and you might be interested in knowing whether that person is going to be working for your company after 6 months, and whether they're going to make it through 6 months. You might look at, for example, their average handling time, and their quality score, and their average speed of answer in training, and you might want to use that to predict whether in 6 months they will be still in your employ, or they will have either been fired or left. Okay, so that would be an example. Certainly, it's your answer is either a yes or no. Or suppose you're a plant safety manager, a plant HR manager, and you want to know whether or not certain machinists will have a safety incident. Either they do or they don't. And you might want to predict that based on maybe their experience level, and maybe whether they've taken certain quality training courses, or whether they've been out sick so many days or not, and so, or the number of sick days that they've been out, and so forth. That would be an example. Suppose you're in a hospital and you want to be able to predict, you're just discharged a patient, and you want to be able to predict whether that person will be readmitted in 30 days. And you might want to look at the time that it took to discharge them, the type of affliction they had, the type of procedures that they underwent. There could be literally, dozens of variables or even more that you use to predict whether they get readmitted. So there's an example. And in fact, you may be able to find out that certain variables have more influence on whether they're readmitted or not. And then you can use those variables in process improvement to increase the probability that a particular patient or all patients will not get readmitted in the future. Okay, so there's an example. If you work for a healthcare insurer, maybe, or a life insurer, you might want to look at, given certain conditions like a person's experience, or a person's age, or a person's coverage amounts, or a product that somebody buys, you might want to be able to predict with some degree of certainty whether or not that person would make a large claim within the next year. Or if you're working in making weather predictions, you might want to say, you've seen some storms you've seen a storm in the Gulf of Mexico, and you want to predict what is the probability that this is going to make landfall in Texas. All of those are great or are good applications of where logistic regression could be used, and it could be used quite effectively Hopefully you've seen the wide applicability of this. I should say that there are other types of this sort of regression. There's ordinal regression, and there's nominal regression. We aren't going to do those, okay? But this is essentially cat Y's with more than that are not binary. So, for example, I might want to. We didn't even give the election example, but I might want to give certain conditions in the. I might want to look at certain conditions in the state, like the unemployment rate, current interest rate, national interest rate, the median price of a house, and maybe even certain polling data. Who knows? And I might want to use that to predict, what is the likelihood that a Democrat will win? What is the likelihood that a Republican will win a congressional seat? What is the likelihood that an independent will? What is the likelihood that a Green Party would? So I might want to do those for more than two, more than just binary. We're going to focus on only the binary in this section. Okay? So that's what we're going to focus on. And the way that we'll do it is we'll just give a couple of examples in Minitab. Now, Excel Stats doesn't do this, so we won't do it in that. We'll stick to Minitab. Before we do, I just wanted to say that in general, you might think that you just start out with what we already know. Well, what if I take a model like y equals b0 plus b1x plus b2x2, b3x3, and so forth, and fit that model? The problem is it turns out that, well, when we're trying to do a probability, probabilities are between 0 and 1. And so if we build a model like this, we either have to really stretch and pull and get all the x's in line, or we have to do something with the y's. All right, so it turns out that it's better and makes a lot more sense to do something with the y's. And the typical definition is what we do is we use a cumulative distribution function. Now that may sound a little bit strange to you, but I'll explain to that. Oops, what that is in just a moment. Sorry, went white there for just a moment. A cumulative distribution function. This is f of x. I'll write it in there. This is f of x. Okay, f of x goes from 0 to 1, and every number in between as x increases somewhere between minus infinity and infinity. So somewhere for some values of x, it flips over from going 0 to 1. So it has that property of only being between 0 and 1, which is kind of good. Now, if you don't know what it is, if you think about some of the distributions that we looked at the frequencies, right? The PDFs. We're not talking about this. This is the CDF. And if this is x, and let's say x is, in this case I've drawn what would be what you probably might think is a normal distribution, and this is some value b in x. It could be 2 or 3 or whatever. It could be 0. In this case, it looks like it's about maybe, say, 3 if this is 0. The cumulative distribution actually is the function that tells me the following. It says f of b is equal to the probability that x is less than or equal to b. In other words, it's the area to the left of whatever b is. And if I drew b over, if I had a different letter, say a, the cumulative distribution would be less. You could see if I drew it in the middle, then the f of, let me do this one right here. And if I called that mu, you'd see f of mu for this case would be 1/2, right? Because that would represent half. Okay, so that's just what it is. And so it turns out that that might be a logical thing to do. It turns out that it works out pretty well. All right, now here's where the real math comes in, and where we make a specific choice of f. So far, so good. It's just we need to find a function that's defined on between 0 and 1. That's defined for all x's, right? So x can be any value, and it just converts the y to be between 0 and 1. Now let's suppose we chose the following. We chose a function such that the probability that y is equal to 1 given on this, which is really f of x is equal to 1, is equal to 1 divided by 1 plus e to the b0 plus b1x plus b2x2, etc. And we'll take a look at that on the next page. What if we did that? All right, so I promise this will not be that long. If you don't freak out, okay? So if you don't need to know it, you're not really interested in algebra, that's fine. If you just want to use Minitab, that's fine. It'll take you pretty far. And when you need to know more, you can contact somebody who's really good at algebra, or you can contact me, and I'll give you my contact at the end. Okay. However, suppose that we wanted to do the following. We set the probability that y is equal. We said p equals the probability that y equals 1. Remember, that's that f of whatever, f of x, right? So what if we chose this specific f of x, 1 divided by 1 plus e to the this. Now you should recognize this, whatever's in this exponent here, as, oh, that's our linear equation. Okay. Now why did I choose that? Well, it turns out that if you choose an interesting function called the odds ratio, p divided by p, well, I'm sorry, by 1 minus p. Now if you think about it, the y equals 1, if p is equal to the probability that y equals 1, right? P is 1, then if we take a look at, 1 is something happens, right? An event happens. The patient was readmitted, okay? So what would be 1 minus p? Well, that would just be 0. The patient is not readmitted in the example that we gave. So p divided by that is just the odds ratio. If you're familiar with horse racing or betting on that sort of stuff, I'm sure you've heard somebody says, well, this horse is a 3-to-1. Okay, well, that means that it's 3 times more likely to do something than to not do something. If your odds of readmission would be 3-to-1, that says that the likelihood that this person is readmitted is 3 times more likely than they would be not readmitted. Does that make sense? Hopefully it does. Okay, so it turns out that then if we take that odds ratio, which is just the ratio of this to 1 minus this, and we take the log of that, we can use some properties of logarithms and expand that out. And if you want to go through the algebra and do it yourself, I think that's a good idea. But if we expand it out, you get this. And then just plugging in the definition, you get this. And lo and behold, some amazing things happen. This one, it turns out to be the same as this. So those cancel, and you're left with just this, the minus log of e to the minus x beta. I've called this whole thing beta. And you'll recognize that this is just the inverse function of the log. So it's minus x beta, which is just x beta, which is just this right here. So it turns out that the log of the odds ratio is just that linear equation that we had before, that we've been fitting before. So mathematicians love when that happens, when they can convert something that looks like a problem that they've already solved. So that's exactly what's going on. We will fit this right here instead of our original y. Okay, now that's going to be okay. I'll show you how to unravel it all, but most importantly, I'll show you how to, how to let Minitab unravel it all, and we'll see that it all works out the same. Okay, but that's some of the theory behind it. If you didn't want to hear that theory, I guess you can skip this next time or whatever. But now at least you've seen it and you know where it comes from. Okay, let's go on, and I want to just do an example. The first example that we'll do is one on programming, which is the one that's in the book on slide 142. So if we look at the slide 142, what I've got here is no, not that. I want to go back to there. There we go. Okay, let's take a look at that. And on slide 142, we've got my outcome here is a success on a task, on a programming task. And it turns out that that's either a 1 or a 0. You see that? There's the 1 and there's the 0. So it's either it's a binary y. It's a cat, and it's either a 1 or a 0. And I want to see if I can predict that by looking at the month's experience, okay, which is a cat. So I have one cat, one num. There it is right there. See, these are numbers. All right. So I want to build a logistic regression to help me predict that. So because I might be a, I don't know, I might be an IT manager, and I have to give certain assignments giving to different people, and I want to predict who's going to be good on which task and so forth. I want to see if I can do better than just my intuition. So let's build a model. First thing I need to do is get into Minitab. Oh, I better open up Minitab. How's that? Come on, Minitab. There you are. Okay. Now I've got it open. Copy. And this is a fairly simple one because it's just one predictor and one guy over there. So we're going to do this pretty quickly, and let's just start out with regression. And here it is right here. Here's our binary logistic. You'll see underneath it is ordinal and nominal. You can look it up if you want to use those, but let's just start with binary. We'll put in the response is success. The model is months of experience. Now, if we had a categorical factor, we would put the categorical factor there. We'll do that in another example that's coming up right away. All right. We won't need to be messing with the options, but just in case you were interested, the function that we actually looked at was called the logit. Remember that thing with the e's and all that? Turns out that there are others that people can do as well. There's a probit / normit, and there's even a gompit. In case you are really interested in that stuff, you can click on the help and find out, or you can Google it. We're just going to use the default. In prediction, just want to show you, we'll be able to make predictions, and I'll show you how to do that. Graphs, we're going to want to click delta chi-square versus probability. Let's not worry about y. It's a diagnostic plot, very similar to residuals. We use it to look for outliers. And let's see, results. We're going to leave this at its default. And finally, storage. There's lots of things that you can store. I recommend storing the event probability, and I recommend it stalling for all observations. And you'll see what that is in just a moment. Yeah, you'll see what that is in just a moment. Okay, I'm going to let it rip now. Click OK. And here it is. So with our residuals, we're going to be mostly concerned about not the patterns, but the outliers. And in the future, what we'd be able to do is use this to see for these outliers, what is it that we're really looking at, and how can we maybe flag those and find other information. So for example, when we did this, we can look at, it looks like this guy in row 2 had 29 months and failed on the task, and this person had 8 months. This guy right here had 8 months, and he succeeded. That's this guy right here, 8 months, and this is 29 months and failed. So that we could improve our model perhaps by understanding why those failures occurred. Maybe this person who had only 8 months of experience had actually done a sorting problem before, and he was giving a sorting problem. Whereas this person was also given a sorting problem, but he had never done it in his 29 months of experience. So that might be it. I just made that up, but we'll find that if you want to improve the model, that's where you would try to focus. That's one of the ways that you would try and focus. Okay, take that out. Okay, so let's go to the top here, and here's if we go in the session window, this is what we see. So first of all, let's just walk through the response here, or the output in Minitab. Tells you it's a logit link function. That's really helpful. Summarizes a little bit, so it says there were 11 ones and 14 zeros, so 11 successes and 14 failures on the task. And then it comes down to here, and this is kind of the key table right here. This is very similar to our table that we used. This is called the NOVA table, or a coefficient table. And this is very similar to our to the one that we had when we were looking at p-values for multiple regression. And that's what we're going to do here. You'll see that the constant is significant. We're always going to keep the constant by convention anyway. And it also gives the months of experience. And it shows that this is also significant, right? The p is less than 0.05. So we're going to keep both of these coefficients. Now, in just a moment, I'll show you, well, let's interpret this just a little bit. Let's do this right now. What the heckle? Okay. What this really says is that for this, I'm going to look at this for just a moment. This model that was just built is an interesting model. It's not for y, it's for our log of p over 1 minus p. Remember, p is the probability of success, the probability of a 1, which means that the task was complete, is equal to, and I'll write it down, minus 3.05, oops, I'm sorry, 3.06, plus 0.16 times ME. ME is the months of experience, right? So this says that for every month of experience, I increase that odds ratio by 0.16. That's it. That's what it means. Okay? So I plug in the value of ME, and I get out the value of the log of p over 1 minus p. Okay, we'll unravel how to change this into a probability that the task is successful in just a moment, okay? But I just wanted to show you what this equation was. Okay, let's walk on through a little bit. We looked at that diagnostic. Down here they have Goodnessoffit tests. You can pick whatever one you want. Pearson one's fine. This essentially just says if the fit is good, the fit of the logit, if it's okay, and we're not going to be concerned about the fit of the logit unless this is a low value, less than 0.05. Essentially, the null is that the probit is that the logit is a reasonable model, and the alternative is that it's not. And here we failed to reject the null. Okay, I'm going to go down to here, and even though this doesn't look like an R squared, this is an equivalent, or a semi-equivalent, I would say, of an R squared. All of these are, but Summers D is the one that I usually use. And Summers D essentially is a number between 0 and 1. The closer it is to 1, the better, the more adequate the model is, the better for prediction it can be. Okay? So that's very similar to an R squared in regression, where when you get a high R squared, it has good predictive value. For Summers D, the higher that is, the better. This is moderate. I'd probably want to improve that, but it's not terrible. If I had about 10% or 20%, I definitely would want to add more variables in to see if I could improve my prediction. Okay, so that's it. There's our model. There's how good it is. Let's go ahead and predict some probabilities. Now, I'm going to hit the Control E again. Oops. No, I'm not. I'm going to go back into Stat, Regression, Binary Regression, and get rid of that graph. I'm going to show you again that when we clicked on Storage, remember I clicked Checked Event Probability. I wanted to store the event probabilities. Those were stored right here. So this essentially says, for this person with 14 months of experience, here's what I would have predicted his success, his probability of success on a specific task was, 30%, and so forth. So if I give him another task, that would be my prediction, 30% chance. Whereas this guy with 29, I would predict 83% chance that he would. Let's see what that looks like, which is just essentially unraveling the function and seeing what the function kind of looks like, our probability function. To do that, I'm going to look at the scatter plot of this output. And let's look at, I'm going to look at my ePro versus months of experience. And just for fun, I'm going to look at the task success versus months of experience. I'm going to put that on the same plot. You may want to rewind the tape on this one because this is kind of a useful one. Click on multiple plots, overlaid on same graph, okie dokie. And there we have it. So this is the actual data that we have, the ones and the zeros. That's given in red. And this line right here, is our model. That's our model for not from the model of the log of p over 1 minus p, but rather this converts this to the model for p. In other words, the probability that y is equal to 1, the probability of success of a successful task. So this would say, for example, that if I had 25 months of experience, that I would predict that this particular IT professional, if I could draw straight, would have about a, I don't know, let's say 67% chance of success. I'll use the Minitab thing in just a moment. About a 67% chance of success. And a 30 months experience, I would say it's about 80%, maybe a little bit higher. Okay? All right. Likewise, 15 months, only about maybe 33% or something like that. Okay. One way to do that in this, an easy way to do it would be to just click on the crosshairs. When you click the crosshairs, you see if you look in the upper left-hand corner, it actually gives you the value. Like this, for example, is at roughly 20. It says there's about a 54% chance. Okay. Now let me just show you in what I did was I did a little of the math for you, and we're going to use this to check Minitab, and we're going to I'll show you how to make predictions in Minitab. But essentially, I wrote this out and back solved for P, and I'll just show you this. I'm only going to do it once. So you'll notice that this is minus 3.05 and 0.16. So if I put that in here, here it is right here. Here's my model. This says, remember, the model is, my model is this guy right here, the log of p over 1 minus p is equal to a constant, minus 3.06 plus 0.16 times ME, right? So that's this right here. Okay, that's this guy right here. So when I do that, I can exponentiate. For those of you who know, the inverse of the log is the exponential of that log. So if I take the exp of this guy, I inverse this, and now it's just a question of solving this algebra equation for p, and that's what this is right here. So this says with 21 months, I have a 58% chance of a probability that a subject scores a probability of success, probability that the person scores a 1 on this. I've got that written incorrectly. This should be a 1 on task success. Okay, and if I do 25 months, 73% chance. If I do 22 months, 62% chance. If I do 1 month, 5% chance. 2 months, 6%. Okay, so you get that basically. Okay. So let's actually have Minitab do this because you might not always have me to help you unravel the equation. So let's get Minitab to do it. For Minitab to do it, that's in regression, binary, prediction. All I have to do is type in the number that I want. So for example, if I want, let's do 20 months. Click OK, click OK. All right, I keep forgetting to uncheck that. And here it is right there. See, it says new observation 20 months. There's my new observation probability. It says 54% probability. Even gives a confidence interval for me, which is kind of nice. And that's it. Let's check to see if we got that all right. It was 20 months, right? There it is, 54% probability. So all is right with the world. Math really does work. And that's it. So we could use this to predict. If we wanted to, we can improve the model. It's a good place to start. That's a lovely thing about mathematical models. You can start and get a good one. You can always make improvements on it. And that's one of the lovely things. And you can also use it to help improve processes, to make predictions about how processes will improve if you do X or Y, if you do this or that. Okay, I'm going to do one more example. And in this one, it's a little bit more complicated. So in this one, we're looking at predicting resting pulse of somebody. I'll call that RP, and whether it's low or high. Now, I know we could actually look at the actual pulse of a person and figure out what that pulse is and say beats per minute or something like that. But in this case, we're looking at a binary, and that might be helpful for just sort of basic screening. You know, given certain attributes of a person, what would be the likelihood that they would have a low or a high resting pulse? Okay, the two attributes we're going to look at is whether or not they smoke, I guess it's called smokes, and what their weight is. So the interesting thing, in pounds, and so you'll see that this is a num, and this is a cat. But we're doing a pretty general case here. We could certainly add more variables, but we're getting essentially all the things that we need to. All right, so let's go ahead and do this. And I'm going to give you one little trick before we, or as we do it. The first thing is, let's put this into Minitab. You'll notice that unlike the last time, remember last time we had zeros and ones, here we have low and high. Minitab has a slick way of creating those into zeros and ones, so let's do that. I'm going to copy, and, oh, right. And, you know what, I'm just going to get rid of that, and I'll put in a new, paste it in. There we go. Okay, so now I've got the data into Minitab, and we could use this directly. It turns out that Minitab can handle this. The problem is, how does it determine what gets a 1 and what gets a 0? Does it assign 0 to the low or 0 to high or what? Does it look for a keyword? Is it alphabetical? You know what? It's best just to fix the zeros and 1 yourself. So here's how I'm going to do it. If we go to Calc, make indicator variables, you'll remember this one. If we go to resting pulse, let's just click on that. You can see it calculates high and low. And we're going to use high. I don't need low, so I'll get rid of that. Delete. And you see that this is, I'm just going to call this RP high. Make it smaller. There we go. Okay, and you'll see that when it's low, it's 0, and when it's high, it's 1, right? So here, what I'm really interested in is I want to set P equal to 1, right? So if you do it this way, you're guaranteed to always have the 1s and 0s correct, which is good. That way you always know what's a 1 and what's a 0. Turns out to be very helpful. All right. Let us, as the rabbit said, go ahead and do our binary logistic regression. I'm going to hit F3 to clear it all out. If you hit F3, it just clears out all this and all the submenus. Here our response is RP high. And our model. Here's where it's going to be a little bit different. In the model, we have to put both smokes and weight, all of the X's. But in factors, we simply have to put smokes. If we don't put anything, it's going to, I'm going to make this mistake on purpose. It's going to complain loudly. Whoops, Minitab didn't like that. All right, so let's do it right this time. Let's put in smokes there, and we should be good to go. Again, I'm going to check my delta chi's, and I'm going to store the event probabilities, just like I did before. Click OK. And again, I have a couple of different outliers right here. I'm going to look at them right away. Again, I'm going to hit the brush. Brushing is a cool tool for this kind of stuff. Set the ID variables. And I'm just going to see what their resting pulse was, whether they smoked, and what their weight was. So who are these outliers? Well, very interesting. I have people who both have a high resting pulse. They're non-smokers, and their weight is not maybe what you would predict. So it's sort of maybe either low or moderate weight people. Okay, so that's where that is. If you want to look at some of the others, like what would be in here, these are people low resting pulse, non-smokers. There's one smoker who's very heavy, or relatively heavy, very heavy, but certainly heavier than the others. Look at some of these others. Low resting pulse, smokes, moderate weight, and so forth. Okay? All right. Anyway, we would use this if we wanted to, say, improve the regression. We might find out that there are certain characteristics of these outliers that we could maybe add in variables for. Let me get rid of it for now. And let's just see how our regression was. Here we are. Okay, the first thing we ought to notice is that in our data set, there's a lot more low pulse people than high pulse people. Okay, that's just something to note. You know, you might want to see if you can sample a little bit differently next time. All right, let's take a look at our model. There's our model. Look, it has the p-value here for this is not all that low. There's the coefficient for that. There's the constant. Here's the one for smokes. This is significant. We keep the constant anyway by convention. The one for smokes or doesn't is significant, and the one for weight is also significant. So both weight and whether they smoke is significant in this. So in this case, we get our log of p divided by 1 minus p is equal to 1.98 plus 1.19 smokes plus minus 0.025 times weight. Okay, so that's our equation that we're going to use. Now remember, smokes is either a 0 or a 1. Either I smoke or I don't, but weight is a number. I'm going to plug in 140 or 180 or whatever. Okay, so that's where that's coming in. We'll do some predictions in just a bit, but let me finish up by this. The fit of the logit looks okay. Oh, my Summers D is not very high. I'd like that to be higher. Maybe in order to get it higher, I could check into those, remember the outliers on the delta chi, those couple that were up there. You know, those up there, I might want to check into those on the delta chi. Or I might also simply want to diagram out a little bit more. You know, maybe I looked at smokes and I looked at weight, but, you know, what would be some other things? Oh, I didn't look at gender. You know, I didn't look at how often they exercise. I didn't look at whether or not they take, I don't know, Lipitor, etc., right? So I can look at all sorts of other variables to try and make that one get bigger, that Summers D go closer to 1 and make this a better predictive model. I can do all sorts of things like that. We're going to not do it right here, but you'll understand how to do it. Okay. So now we fit the equation. Let's go ahead and make predictions, although we'll realize that the predictions may not be very good. Let's go ahead and make some predictions. So to do that, we go to regression, binary logistic. Again, in graphs, I'm going to take out the delta chi because I don't want that keeping coming up. Let's make a few predictions. Let's, okay, I'm going to make a mistake here on purpose, but if I wanted to say they do smoke and they weigh 140 pounds, what would I predict their whether was the probability that they had a resting pulse that was high? If I click OK, it's going to complain at me. It says new observations must be the same type as the predictors. Well, if we look over here for just a moment, where my spotlight is, you'll notice that smokes is yes or no variable, and I put a 0 or a 1, and yes, it's that touchy. So we have to actually do that. So let me put in, instead of a 1, let me put the quote yes. So this is a smoker, 140 pounds. Click OK. Click OK. And there we have it. There's my new prediction for that. It says 42% probability that that person will have a high resting pulse. Okay? Hopefully that makes some sense. Here is what it looked like. Oh, I should just show you, I did this also in here. I put in our model. This is the model that we got. Here's the log of P minus B. Here's the smoker of 140. There's their 42%. See that? Well, we could look at all other things, like what happens if they were a non-smoker. Oh, you can see the probability that they have a high resting pulse goes down. Okay, so smoker has a lot of prediction. What happens if we looked at a smoker who is 120 pounds, 54% chance. Smoker who is 110 pounds, 60% chance, and so on. Okay? So, so that's basically it. If you wanted to kind of get a picture of this, remember I had also, keep doing that, remember I had also asked to print out the probabilities, and that's given right there. I've done it a few times, so it printed them out each time. We needed one. And I might want to plot this versus, say, weight and whether or not they smoke. Let me show you how to do that. Gives a nice little picture of what's going on. Here I'm going to do a scatter plot with groups. I'll do with connect in groups, and you'll see it kind of is interesting. I'll do ePro by weight, and then I also want to put in the categorical variable of smokes. Check this out. It's a cool plot. And there you have it. This is pretty good because it kind of shows, here's what the function is for a smoker. Here's what the function is for a non-smoker in terms of that probability. You can see that the heavier they go down, the lower the probability that they have a high resting pulse. And if they're a smoker, that probability increases. There's just like an offset for the increase. Oh yes, one last thing I wanted to show you before I go on. What would have happened if I just automatically did low resting pulse instead of making that indicator variable? What if I just did that in my model instead? I'm going to show it to you. With some trepidation, I'm going to show it to you. No, I can't do a regular regression. I'm going to go stat regression, logistic regression. Again, F3 it and clear it out. I'm going to use resting pulse here. The model is smokes and weight. Factors are smokes, just like we had before, except now it's not a 1-0. Now it's a text variable. And remember I said all bets are off as to what is a low, what's a 0, and what's a 1? You'll notice that it gives all the same, it gives the same model but with negative signs on the coefficient. So it actually chose the low value to be 1 instead of high. The value, quote, LOW, it chose to assign, Minitab chose to assign LOW as equal to a 1 and HIGH equals 0, and we would have never known that. We would have to figure it out from kind of looking at the equation and checking it all, using predictions and stuff like that. Whereas if we control it by doing the indicator variable first, we know what's a 0 and what's a 1. It really is that simple. Okay. Well, that's it for binary logistic regression. For binary logistic regression, hopefully this gave you a pretty good, we went over some applications, right? Pretty good indication that this is pretty useful stuff. This is when I have a Y that's a binary outcome, right? It's a cat, but particularly it's a yes or no variable, and I can have multiple x's of any sorts, x1, x2, x3, and these can be cat or num, whatever I wish. Lots of different applications of that, from healthcare to manufacturing to elections to financial services. Applications everywhere. This is a case where you have an outcome that either happens or it doesn't. I readmit the patient or I don't. The member makes a claim or he doesn't. The machinist has an accident or he doesn't. Okay? Lots of things there. And then we went through a couple of examples, right? We went through the example of the programmers and also the resting pulse. Okay. All right. Well, I hope you learned something, and I hope you give it a try. And if you need any help, do not hesitate to contact me at mzabel@straightlineps.com. All right. Take care.